So welcome, everyone. Welcome to today's session on system integration for miniaturization of a cold quantum device hosted by both OptoSigma and ColdQuanta. Many of you know who I am already. My name's Cindy Gong Harris. I'm the Business Development Manager for OptoSigma, and I'll be hosting today's webinar. I'd like to introduce today's presenter, Dr. Clinton Cahall, who is a quantum engineer at ColdQuanta, where he leads efforts to develop miniaturized, robust hardware infrastructure for scalable trapped ion quantum technologies. ColdQuanta manufactures and integrates cold atom and miniature ion trap packages and systems. OptoSigma manufactures optics, optomechanical parts, and stages for both standard and custom applications. We are recording today's webinar, so following the session, a recorded version will be available to everyone. We'll make sure to answer all of your questions at the end, so please submit your question using the Q&A button located on your Zoom toolbar. For those of you just joining us, welcome. Once again, I would like to introduce Dr. Clinton Cahall, who is a quantum engineer at ColdQuanta. He will now share his expertise. Clinton, welcome, and please feel free to begin your presentation. Thank you.
Thank you. Let me go ahead and share my presentation and screen. Okay, great. Yeah, thank you so much for the introduction, Cindy. And I'm happy to be here and presenting to you all today. Like Cindy said, my name is Clinton Cahall, and I'm here at ColdQuanta. And today I'm going to talk to you about the system integration for this miniature cold atom system, specifically a trapped ion system. So here's a brief outline of what I will discuss today. I'll go through a little bit of the quantum motivations, why we care about building these systems, and a little background about what we do here at ColdQuanta. And then I'll go through the specifics of our trapped ion system and what are the building blocks to create and construct such a system. And then we can end with a live look at the demo system that we've constructed here. So why do we care about building these quantum devices? Well, because the potential for the types of problems that these systems can solve. The possibility of solving some of these important problems such as factoring, chemistry, material science, machine learning, and optimization. These quantum computing devices have the potential to solve these problems in a much more efficient way than we can do on current classical hardware. Quantum computers are fundamentally different from classical computers in the way that they store and process information. We know that on our classical computers, we can store information in discrete bits, which we label as 0 and 1. And these bits are physically usually the voltage on a wire or the charge on a transistor. Quantum computers store information in a fundamentally different way. The way that quantum computers store information is in the internal state of a microscopic quantum system, such as the spin of an electron or the internal energy state of an atom or the polarization state of a photon. And because these are quantum systems, we can store information as superpositions of these states. So this quantum system can exist as in these multiple states at the same time. So this is really what gives quantum computing some of its power. And physically, the four leading platforms for developing these quantum bits or qubits are shown here, which are trapped ions, neutral atoms, superconducting qubits, and 2D quantum dots. And we place a couple more requirements on these qubits to build a good functioning quantum computer. We want them to be well isolated from one another. We want them to be programmable, controllable, so that we can manipulate and process information. And we really need a lot of them in order to be able to do meaningful science. These four platforms can roughly be broken into two categories, which are atomic qubits and engineered qubits. And atomic qubits, by their nature, are identical, whereas engineered qubits are inherently not identical. So if we focus on some of the characteristics of the atomic qubits, we're going to see that we're sort of led into wanting to work with these because they have quite good properties. Typically, they operate at room temperature or modest cryogenic temperatures, as opposed to the hundreds of millikelvin that are required for solid state qubits. The atomic qubits lend themselves very easily to optical interfacing for quantum networking, and we can take advantage of standard laser-based cooling and control techniques. And so it's not surprising that at ColdQuanta, we've invested heavily in working with these atomic qubits. We have a large effort underway to develop a neutral atom quantum computer with hundreds of qubits. And we also develop and provide infrastructure for trapped ion researchers as well. And so that's what I'll discuss here today. In general, here we like to take some of these messy optical tables that you see here, which are probably pretty familiar to those of you in atomic physics, and identify the important subsystems, distill them down, and engineer them really well, and then integrate those subsystems into a complete turnkey system, which is shown here on the right. So this is a quantum matter system, specifically BoseEinstein condensate, where we have everything from the lasers to the laser electronics, control electronics, all the way up to the vacuum cell and distribution optics. And so this is a complete and self-contained system for quantum matter. And now we would like to do the same thing with trapped ions. So the first piece, the first building block of one of those systems is the vacuum package. Typically in trapped ion experiments, the researchers work with vacuum systems that look something like this on the photo on the left. These are large systems, often bulky, and they're usually custom built. At ColdQuanta, we've developed a miniaturized version of this vacuum system that's room temperature operating, and you can see it here next to this to the traditional vacuum system, and you can see that it's a fraction of the size. So this miniature vacuum system has an integrated ion pump with it, so it has active pumping as well as passive pumping. There's a high optical access around the chamber and from the top, and this entire miniaturization process leads it to be very useful for deployable applications, which is one of the goals of this design. And even though we've miniaturized the system, we've still been able to maintain a low 10 to the minus 11 torr vacuum performance. And this is very comparable to these traditional vacuum systems. And in fact, we have one of these prototype packages in operation at Duke University and has been operating for 2 years now. One of the advancements that has allowed us to miniaturize the vacuum package is the development of a surface trap. And so the trapping architecture, the infrastructure is a requirement for performing trapped ion research. Typically, the ion is confined by the electric fields created from this trap. And typically these traps are created out of macroscopic tungsten rods and assembled by hand. In the last 10 to 15 years or so, the development of microfabricated traps has allowed these 3D geometries to be mapped to a 2D microfabricated surface where you can print these traps using standard lithographic techniques. And this has really allowed the trap structure to be miniaturized. And this process was pioneered by our friends at Sandia National Labs. And we can create these trapping potentials over the surface of this trap. And because of this miniaturization of the trap, we can also miniaturize the vacuum package that mates with it. And so I show here one of our sister products, which is a cryogenic version of our vacuum package. And so our room temperature version is very similar to this, but with an integrated ion pump. And so this surface trap has allowed us to do this miniaturization. Next, for building a trapped ion experiment, like I said before, we cool and control the ions using laser light. Each atomic species is going to have associated with it its own unique set of wavelengths that you need to address the ion. In this system I'll talk about today, we use a ytterbium ion. And so Toptical Photonics has created these really nice multi-diode laser racks specifically for ytterbium, where they have the laser light and control electronics in a rack-mounted system. And these wavelengths are 370 nanometer light for photoionization and cooling, 399 for photoionization, and 935 as a repump wavelength. So let me go through just a quick rundown of what the process is for creating an ion trap. First, we start with an atomic target, and we need to release the atoms from that target. And we do that by using a high-powered pulsed 1064 nanometer laser. And this is provided to us by Coherent. And the high-power laser ablates the atoms on the surface of that target and creates a plume of neutral atoms that is directed across the trap. Now, since these are neutral atoms, we can't use the electric fields to confine the ion, and so we must give confine the atom. So we must give the atom a charge, and we do that by removing one of the electrons from that atom through photoionization. And this photoionization is a 2-photon process where the neutral atom will absorb a 370 nanometer light. A 399 nanometer light, and then a 370 nanometer light. They will absorb these 2 photons to kick one of these inner shell electrons to the continuum. And then in that way, we give the atom a charge and it becomes an ion. And then we can use that ion, or we can use the charge of that ion to confine it within the electric fields created by the trap. So once we confine the ion, it still has quite a lot of energy. It's still quite hot. And so we immediately need to cool the ion. And we do that using this 370 nanometer light, which addresses this S to P transition. And through a process called Doppler cooling, we actually shine this laser light on the ion and it removes energy from the system. And this transition is what's known as a cycling transition. So as long as we keep the 370 nanometer light on the ion, it'll keep removing energy, and it'll also, every time the ion moves from the P to the S state, it will emit a photon. And so the ion will fluoresce as long as we keep this 370 nanometer light on it. And in that way, we can image the ion and measure its internal state. And lastly, I mentioned this 935 as a repump wavelength. Sometimes the ion will decay from this 2p1 half state into an energy level that's not shown here, which is outside this manifold. And so we need this 935 to repump the atom back into this manifold to continue the cycling transition. And so we have all of these wavelengths, these 4 wavelengths that we need to route and direct into the ion trap. And so we need a lot of high quality optical and optomechanical components to achieve all of this routing of the laser light into the ion trap. And the requirements that we place on our optical system are, we want a simple beam layout and a minimized optical path length to reduce things such as vibrations and air currents that will degrade the quality of the laser light as it goes into the ion trap. And we also want a stable and high quality optical components to construct a system, especially for deployable applications. For those reasons, we've worked closely with OptoSigma to create the beam paths that are directing the light into the ion trap. And a typical beam path is shown here in this schematic, where we have light coming from the fiber output. It is collimated using an A-sphere collimating package. And we bounce it off of 2 steering mirrors to point and direct the light where we need it. And then we focus the light down onto the atom. And so these lenses, especially, are mounted into these optomechanical components from OptoSigma and then on the translation stage. And here's a CAD layout showing how we've designed the optical path to be as compact as possible. So this mount that we use for the collimation package is actually quite important because we want to be able to have a stable pointing from the light as it exits the fiber. And so we use one of these high stability mirror mounts, which is designed for mirrors, but it also is compatible with putting a collimator in there as well. And the one thing that we like about this is, so it's got a large angular tuning range, but it also has a really great thermal repeatability. And so in those situations where you want to set the setting of your optic and leave it, this is really helpful to have something that is very thermally insensitive. And lastly, what the last component of the optical system is the imaging. And so the imaging system, again, we want to collect the fluorescence from that ion to image the ions and to do state detection. And so typically what is used in these imaging systems is an objective lens. And most of the reason for that is that objective lenses typically have a high numerical aperture, or NA. And the NA is shown here in the schematic. Essentially, the NA describes this cone of acceptance that the objective lens will have. So the ion will fluoresce isotropically in all directions. And so we want to collect as large a cone as we can, to collect as much light as we can. And that's important because the more light we collect, the better we can image the ion, and the higher fidelity our state detection is. A couple of other metrics associated with objective lenses are the field of view. The field of view describes how far we can actually image objects in the transverse plane of the objective. And so this translates to basically how many ions are we going to be able to image in a chain. And then lastly, the working distance describes how close we can get the objective lens to the object that we're imaging. Typically, objective lenses have quite limited working distances. In our application, we want to have a relatively large working distance because we're fundamentally limited in how close we can get to the ion because of the backing package that surrounds the ion. So in the end, we're going to be limited by we don't want to crash into that backing window. And so a large working distance is really needed. So again, we've been able to work with a really great objective lens from OptoSigma, and this lens features well, first it's a near UV objective that actually has compensation for this backing window. It has a built-in compensation for aberrations from that window. It has a high numerical aperture of 0.45 NA, and a large working distance of 15 millimeters. So we're not limited by the backing package itself. And it has a resolution of nearly 0.5 micron, and compare that to the typical ion spacing between ions is 3 to 5 microns. And so we can easily image and resolve multiple ions. And it has a 130 micron field of view, which again allows us to image up to 25 ions, which is great. So we can image a large chain using this single objective. So we mount this objective into a cage system where we have the objective lens mounted with a few filters and a camera. So all of these components are mounted in a single cage, which is really useful because we can adjust the position of the objective without also having to specifically adjust the filters in the camera. So having all of these movements common mode is great for tuning and great for fluctuations such as thermal fluctuations or vibrations. So all of that stuff is going to be common mode in this cage system. And we mount this cage system with a counterweight and can take advantage of one of these 3-axis mounts to again control the X, Y, and Z position of the objective and the filters in the camera. And we have a great resolution on this objective position. And so this is really going to allow us to align and control the optics in a really easy way. So now I will go ahead and show you the demo system that we have constructed here, using all of the subsystems that I've just described: the laser system, the backing package, and the optics. So let me change my camera here real quick. Great. Okay, so you can see that, so we have the system that's built, and this is a 15U rack. It's a little bit hard to see, but below the camera, we have all the control electronics for the lasers, and you can see the laser outputs here at the top. And then we also have the wave meter so we can monitor the wavelength of the light. And it's a little bit washed out, but I have the wave meter up here on the screen at the moment to show that we have the right wavelengths. And at the very top is our control box to send voltages to the electrodes that confine the ions. So I'm going to take the camera and do a little zoom in feature here to look at some of these subsystems in more detail. So we can see here how the objective is positioned right over the top window of our vacuum package. And like I mentioned before, this is where the fluorescence is going to be output from the ion. So this is the port in which we image and do state detection. And then the ports on the edge here, where you can see these windows around the perimeter of the vacuum package, are where we direct the light into the package itself. The DC electrodes are controlled and voltages are sent to the electrodes through these cables here. And we have a miniature RF resonator. I didn't talk about it specifically here today, but those of you who are familiar with ion trapping systems know that that's a key component. And if we take a zoomed out view here, we can see how compact this optical setup really is. And let's take a look under the hood here, and we can see where some of the routing and manipulation of the light, how we've been able to confine that to really just a few square inches. And I'll show here some of the translation stages and the optical mounts that we've been able to use. And again, the system, we've been able to engineer it such that it fits on this top breadboard is an 18 by 18 inch breadboard. And so we've been able to reduce the footprint of these experiments to quite a large degree. Okay, I think that's all that I have, and I'm happy to move forward with questions. Cindy? Oh, I think you're muted, Cindy. Sorry.
Thank you for an excellent presentation, Clinton. We do have a couple questions from our audience. If anybody else has additional questions, please ask them now using the Q&A button. And keep in mind that this will be available in the future to view as a recorded version. The first question is, how do you mount the ytterbium source in the ion trap vacuum chamber?
Yeah, that's a good question. So as we're assembling the vacuum chamber itself, there are a lot of components that go into it. We have sort of the shell of the vacuum package, and we have windows that insert in each of these slots. So the ablation target is actually one of those slots. So we load the ytterbium into that ablation target, which is then welded into the periphery slots of that octagon package. And so that loading is actually happens before we seal the vacuum package onto the trap. So the source remains in the vacuum package, and then the way that we get the atoms from the source is through laser ablation.
Thank you. The next question is, what is limiting the mini ion trapping chamber vacuum? Is there a path for improvement?
Yeah, that's a really good question. Oh, sorry. Yeah, that's a good question. We use a combination of passive pumping and as well as active pumping. So the active pumping again comes through the integrated miniature ion pump, and then we utilize some passive pumping that is integrated into the package itself. And so really what's limiting it is probably just the finite amount of pumping that we have available. There are going to be inherently some trade-offs by miniaturizing everything. We would like to pack more passive pumping or have a bigger ion pump, but this is a trade-off between sort of size and performance. One of the things that cryogenic packages take advantage of is a cryo pumping. So you can do a lot more efficient pumping by going to cryogenic temperatures, but then your system becomes bigger. So In the end, I think there's room for improvement, either both by designing the chamber well, and also improving the performance of the miniature ion pump.
Thank you. We have a couple more questions in a few more minutes. Generally speaking, how much faster would a quantum computer be in comparison to a standard computer?
That's a good question. It depends. It depends on what question you're asking it. There are a lot of applications. There's a reason why. Classical computers is not a tool that we're trying to replace. I would say classical computers, especially the algorithms that have been developed, are incredibly efficient at solving certain problems. Quantum computers have been theorized to be incredibly efficient at solving other problems. And so, one the sort of touchstone example that people give is factoring a large number into 2 primes, which has, of course, this has big applications for encryption. But in general, you can get the biggest supercomputer that you want to try to factor, one of these large numbers, say, a 2000-bit number into 2 primes, and it can take, up to the age of the universe. And depending on the speed of your quantum computer and what your architecture is, you can do that in days rather than thousands of years or millions of years. But again, it's a little bit cherry picking. There's specific problems that are designed that lend themselves to being solved by the architecture provided by quantum computers.
Thank you, Clinton. There's a question about Sandia advising against using the HOA2 trap face up. Have you seen any problems using the trap in this configuration?
Sorry, the question was
just using the trap face up. Have you seen any issues or problems using the trap in this configuration?
I see. That's a good question. I think I haven't heard that specifically. I would default to Sandia about their, I've seen the trap be used in a myriad of ways, really. Either where the imaging is done in the horizontal direction, or from the top or from the bottom. There's I don't know if I know of any definitive evidence of which is the best way to use it. There may be other there could be quite a few motivations for doing for doing either or. I think probably what I would think is the bigger motivator is the larger motivation is how you design your optical system around it. So in this demonstration, we've shown it being oriented vertically, where the imaging is done from the top, but I've also seen it flipped over and where the imaging is done from the bottom.
Okay, great, thank you. We have a few more questions. We're running out of time, so I'll try to answer as many as possible. The next question is, do you know how many ions that can be trapped at the same time in each assembly? And how do you envision that ion trapping will scale to match current transistor packaging densities?
Yeah, that's a good question. I think each component, each ion trap component can trap on the order of let's say 30 ions. There are architectures that have been so with 30 ions you can do some interesting things, but really you want to get to 100 ions to do some start to scratch the surface of actually some simulation science. But for anything having to do with computation, you want to get to thousands of ions. So that's really you're starting to look at some of those larger numbers, and there are proposed ways to scale the number of ions. I would say that from our perspective, so there have been architectures that have been proposed for doing that, where you can connect modules where you have a single ion trap, and you can connect them through optical interconnects, and you connect tens of these modules to create your get to the hundreds and thousands of levels of ions. From our role at ColdQuanta is really just working on the hardware itself, and that's some of our approach for quantum computing that's included in our company is neutral atoms. So you can do lattices in that case, and that's one of the ways that you can use the atomic platform, but scale in a probably a straightforward way.
Are you selling your mini resonators for use with the trap?
We are. Yes. We have that miniaturized resonator. So we've tested it with an HOA style trap, and loaded with the trap capacitance. We've measured a resonance frequency of 45 megahertz, and so we've actually just shipped one of these resonators to a customer, and we're getting some feedback on the performance in trapping itself. But with a surrogate system here, fully loaded with the trap capacitance, we've measured a 45 megahertz resonance frequency.
Great. We'll do a couple more questions. We're over a little bit. Do you need to worry about stray blue or UV light finding its way into the trap with such a small chamber?
Let's see. Do we need to worry about stray UV or blue light? I would, from the ambient environment, no, we don't really need to worry about that. As far as like how it interacts with the ions, I think that's a negligible background effect. There have been studies about scatter from the ions themselves that interact with other ions in the chain, and that's also it's quite small. Really, one of the biggest things that is a limiting factor when you're working with ion chains is individually addressing those ions. And in that case, it's not the scatter from the ions that makes that's really the killer, but it's focusing the light down to a single ion and not having lobes of that focused light interact with neighboring ions. And so that's actually quite a difficult problem. And there have been people that have done studies about the crosstalk between atoms, and they can get it quite low. But I would say that's the bigger engineering challenge.
Okay, thank you. Question regarding the objective lens. It's a NUV lens. Are there many other wavelengths within the trap? And can you talk about what wavelengths the objective is being utilized for?
Yeah, that's a good question. There are several different wavelengths that are going into the trap, but really there's only one wavelength that we care about when we're trying to image the ion, and that's that 370 nanometer transition. And typically for your ion species, so for example, barium, it's a different wavelength. It's a 493 transition, but you're putting all these wavelengths into the chamber to address the ion. That in each of those have a specific role, but in the end, that the transition that you're trying to look at for imaging and doing state detection is typically a single wavelength if you're working with a single species. And so in that case, we really only want to look at the 370 nanometer light, and therefore the NUV has that it covers that range for us. We don't need to worry about what the 935 or what the 1064 is doing.
Great. And let's answer one more question. I know we're not getting to all of them. We do have quite a few from our audience, which we appreciate all of your questions and engagement. The last question is, how soon do you expect to benchmark side and cooling heating rates and things like that with your system?
Yeah, that's so I would say we're not really in the business of doing that. So sideband cooling and heating rates, so our role here is really system integrator. We're making the backing packages, and we're integrating it with the trap, with the optics, with the controls. And I would say that would be something that we would, we would give the system to you, and we would be curious to learn about those performances. In the end, those types of things are going to be dictated by a whole wealth of things. As far as the trapping, what the performance of the trap is, what how stable the laser wavelengths are. So here at ColdQuanta, we're not doing specific experiments with trapped ions. Most of our experiments are centered around neutral atoms, but we do. So our role here in the trapped ion community is to make this miniaturized hardware, and then we can integrate these systems.
Thank you. And it seems like our audience is still pretty engaged. If you don't mind, we could ask a couple more questions.
Sure.
How much laser power is needed at each wavelength?
Yeah, that's a good question. So in the end, we're addressing a single ion, and so you don't. So at the let me say for the 1064, that's a completely different process where we're going to we're trying to ablate material from a metal target, and so we need quite a bit of power in that case. Watts generally. We usually think about that in terms of power per pulse, but in general, it's going to require lots of power. For doing the cooling and such, and all the wavelengths associated with the trapping, it's really it's on the order of hundreds of microwatts to milliwatts. I think in general, what you want to look at is we're addressing a single ion, and so what we want to maximize is we're sending photons, and we want to send as many photons as we can to improve the interaction between the laser light and that ion.
Thank you. Another question is, what is the Q factor of the tiny resonator?
Yeah, that's a very good question. I think that's something that we are actually in the process of learning. The Q factor, in an actual experimental environment, it actually depends a lot on some of the parasitic resistance that is between the resonator and the trap itself, and it depends on how you connect the resonator to the trap, and the trap what the electrical components are like. So we actually in designing our system and testing it here, we use a surrogate system, and so we were really measuring the resonance. It looks like some of the early preliminary experiments that have been done, the Q factor is on the order of 55 to 75, somewhere in that range. And again, this is the first of these miniature resonators that we've produced. So we're looking forward to getting some feedback and iterating on that design.
Great, thank you. A few more questions. We're trying to get through all of these. What NA do you have from the side windows for optical addressing of individual ions?
Yeah, that's a good question. So the side windows have a 0.12 NA. So we have a 0.12 NA for there's one position that has a 0.07 NA or so, but typically that when you look at the geometry of the package, that window is that type of access is fine for typically what you're doing through that window. But through for example, for the transverse plane, or for the angle that is transverse to the trap axis, that's a 0.12 NA window.
Great. And a follow-on question about the side windows. What determines the glass thickness on the windows of the vacuum cell?
That's a good question. The glass thickness is there's not necessarily I would say the glass thickness is determined not from an experimental perspective, but more from an engineering perspective. you know, it's a trade-off between sort of the structural integrity of the glass and how well we're able to get the surfaces flat and polished. You know, ideally we'd like to be able to go pretty thin, but again, we have to assemble this window inside this vacuum package and be able to weld it into the package itself. And so that determination is more of a manufacturing and engineering type of decision rather than a purely you know, something that's motivated by the optical performance, really.
Okay, great. And the last question is, do you have any suggestions for resources to learn more about optical control of these atomic quid bits, particularly from the quantum simulation perspective?
Yeah, that's a really good question. You know, I think there are probably a lot of online resources, especially universities have a lot of online resources that are available. You know, going through some introductions for the atomic physics. I think you know, our own company has put out sort of a web service where you can control not ions in this case in our case, but neutral atom quantum matter, where you can actually control some of these you know, some of these quantum experiments via cloud access. You know, so for at least from a quantum simulation perspective, and I know other companies are doing this too, and we're happy to do that as well, where you can actually, you know, get some of this perspective and this experience controlling these systems by actually doing it, you know, via cloud access. And so that's something that's really exciting that's come along in the last 6 months to a year, and is a new introduction for our company as well. So we're happy to, if you have any more questions about that, we'd be happy to answer.
Thank you. And I appreciate everybody staying on longer than the scheduled time. It was a really great webinar, Clinton. Thanks again for everything. If you have additional questions, feel free to email sales@optosigma.com and we can forward to Clinton, or you can email ColdQuanta as well. Once again, there will be a recorded version of the webinar. And, you know, once again, we did partner with this project with Toptica, Coherent, Duke, and Sandia National Labs as well. So we want to thank them for providing parts and the technology to make all this happen. I hope that everybody's enjoyed today's session, and thanks again for joining us.
Thank you, everybody.